sort of bringing this thought to mind. He approached me, I think about 2 weeks ago, and asked if we could have a short session to discuss how we employ machine learning in the industry and discuss potential applications that we have in process engineering and chemical engineering for that matter. I know we've already taken 10 minutes of our time, but what I'm going to do is I'm going to share some few slides, then we sort of discuss through some basics of machine learning and share some ideas on areas that machine learning is applicable in process engineering and chemical engineering in general. Please permit me if I'm not giving like very detailed information on this matter, because it's like I'm not able to kind of share exact like work that I've done before, so I kind of try to be as very general as possible, but also try to capture something that will be more meaningful to you. So with that said, I'm gonna share my screen, and then I think Richard, your Google Meet sort of suggests I'm not allowed to share. Is there some security settings you placed on the meeting call?
Please, you can share it now.
Okay, awesome. Yeah. All right, I'm gonna share the entire screen and let's go. All right. Do you see my slides?
Yes, sir.
Okay, good. So in this what do you call it talk, we will discuss some very few basics about definitions in machine learning, just to introduce ourselves to what it's really about. Then we also talk about types of machine learning models. And then in that, we also discuss some of the commonly used machine learning models in the field of chemical engineering based on research. And we also discuss how to develop a machine learning model from start to finish. What are the decisions involved? What do you need to know? And then we'll talk about what are the common processes in chemical engineering applications that machine learning can be useful. All right, machine learning in general is not a new thing. I think the development of machine learning dates back way to, I think, the early 1950s. I think around 1957 was when the first perceptron was developed, so to speak. But just that it took a very long time for us to get to where we are today for a lot of good reasons. But we are now at a stage where it's become very cheaper and much easier to be able to develop models and actually action them. But broadly speaking, machine learning and artificial intelligence all fall under data analytics. Just that the more complicated you get, then we sort of classify that level of complication into a different name. So for instance, let's say you are interested in finding out what do you call it, what's the average age of a student being admitted to KNUST. It's much easier to just sum up the ages in the school and divide by numbers, and you figure out, okay, the mean age is maybe, I don't know, 19. That in itself is data analytics. But if we were to change that scenario, you sort of able to figure out all the factors that affect a student's ability to attend um, university and Kenya University for that matter. And you are able to use that data and develop a sort of model to be able to predict the mean age and forecast out what is likely going to be 10 years down the road. Then you start shifting away from just doing like a handpick numbers and averaging to more of a forecasting sort of model. And in that case, we call that a machine learning model. In the olden days, that would have been called a regression model. So if you speak to a statistician who might not be so interested in AI, they'll make fun of you. They'll tell you that, what do you call it? Machine learning engineers are disappointed statisticians. Um, but it's generally true. The two are basically uh, uh, the same, but quite different in the sense that with machine learning, you providing some level of computation into the picture. Then within that broad class of artificial intelligence, which is probably the most common word you probably have heard for the past couple of years, is what we call the machine learning. And within that subset of machine learning is what we call deep learning. And now we are currently at generative intelligence. So you probably have heard the word thrown around, generative AI, but that is where we are. But they all fall under the umbrella of machine learning. These are some of the most common machine learning models that you can find out there. And generally, machine learning is sort of grouped into three main buckets. One of the buckets is what we call supervised learning. Supervised learning, in this case, is more like a guided learning, so to speak. Generally, you have your data, and you cannot talk about machine learning without data. Data is the life and blood of machine learning. Yes. Yeah. So supervised machine learning in general deals with the type of data and type of problem that you want to solve. So in general, when we talk about supervised machine learning, we're talking about what we call labeled data. Labeled data is data that know what the end goal. When we talk about supervised machine learning, we're talking about what we call labeled data. Labeled data is data that you sort of know what the end goal is expected to be, and that end goal is say is inside the data. If we bring it to, let's say, our chemical engineering context, a labeled data might be something like you are measuring like flow rate of a certain liquid, and there are different factors that are going to influence that flow rate, right? So for instance, you might be right within the pipeline, and then so you have a label for each set of parameters case, which might be your pressure, the scale taken pipe, that, and you know what the flow rate is. So in that case, say and will go for maintenance because there's too much scaling in the pipe. So that's where machine learning becomes useful to you, in the sense that you can use that information that you have to actually slow down your, that might not be economical for you to keep operating. So that's where supervised learning comes in. There are different models that can be used in this, what we call the k-nearest neighbor, the naive Bayes models, which are based on the Bayes theorem. We have decision tree support vector machines, and under that too is networks. And there are various forms of it. We have what we call a convolutionary neural network, and then the long short-term memory neural network, mostly used for time series-based data is where that's very useful. Then we have the second set of machine learning called machine learning. In this case, you are not aware what your target variable is or what your label is. So you are kind of interested in the data to be able to group your data into certain buckets and figure out what those buckets really mean to you. So they are normally used in areas like clustering, pattern recognition, and you can also use them in like clustering like some sort of signals in that case. And you can also use some of those in what we call the PCA, principal component analysis, which in the layman terms is a dimensionality reduction. Because when it comes to machine learning, it's more about how much data you have, how heavy data you have. But there is also that problem you face when you have too much information. Then the model can overlearn to the extent that it's basically memorizing itself. And once it becomes a memorized model, it's not that good. It's like that student might be able to just memorize everything and go and score, but after the exam, there is it. You show the student something else that might not be exactly as what they memorized, and they forget and basically recall what they have memorized and give you that. That is where things like PCA can help out. PCA is basically saying, okay, there's just too much information that can easily overfit this model. I want to reduce that level of information, but I have no idea which one is the good information. So you have that sort of dimensional reduction algorithms that will go in and say, okay, well, for the 20 parameters or the 50 parameters you have in the data, I'm going to take it from that 50 dimension and transform it to sort of say a 3-dimension. So you end up with 3 parameters in your data set. But those 3 parameters contain the information that I would say all the information, but about 98% of the information that the 50-dimension data set might have. So we use supervised learning in most of those cases and Gaussian mixture models. We also have the other area called the reinforcement learning, and that one is mostly used in policy-based, what do you call it, systems, like a self-driving car might use a reinforcement learning. Uber, for instance, uses reinforcement learning. Google Maps use a lot of those reinforcements learning because it was weight-based system. And you can see here in the case of how like you create like clusters, basically groups of supervised learning. There's another type of machine learning that's normally not called out, but it's called a semi-supervised machine learning. And that semi-supervised machine learning tends to be based on the sort of problem that you want to solve. For instance, if I have, and this was something that I had to do last year, you have a problem where you're trying to figure out what sort of information are people talking about a certain product. So you're able to go in, you use some unsupervised learning, you learn about that information, and you group them. Say, okay, well, the people are talking about 10 different things about this particular product. And you label those things from 1 to 10. Then when there's new information come in, you want to be able to just predict which of those 10 things people is the new information about. In that case, you have transitioned yourself from using the unsupervised machine to derive the 10 things. Then you not train a model to now be able to predict those 10 things. So with new information, you have transitioned yourself from unsupervised machine learning to supervised machine learning. And that's what we call a semi-supervised machine learning. Some common machine learning models are used in chemical engineering, and this is actually based on a literature review compiled by you. And it's quite not surprising to see what the models are in terms of what is commonly used. He found that 22.9% of the literature that he gathered were using artificial neural networks in those processes. Then the next in the line was support vector machine and random forest. Random forest models generally tend to be good. The challenge with them is that they tend to overfit easily, so you have to be very careful if you are using them for any sort of analysis. And they are mostly like tree-based learning, so like more like a bag of decision trees, basically. And then most other algorithms, they were using more like genetic algorithms, gradient boosting, which are all like the tree-based learning. Well, what were the issues that these chemical engineers were using? Whereas now, yes.
I see you're not moving the slides. Can you check on that, please? Thank you.
Really? Wait, it's still not moving?
It's okay now.
Oh, okay. I think it's probably too slow there. The Google so most of these researchers have been using this for more like prediction, like we talked about, for instance, prediction flow rate for your pipeline, optimizing whatever system that they're trying to build, identifying things and classifying things into groups, characterizations. In this case, a new upcoming area of what do you call it, AI in chemical engineering is material discovery. And I think just a couple of weeks ago, I think Microsoft had what we call the Azure Quantum Compute, which sort of a high compute platform for material discovery, where scientists were able to use that, and based on material chemistry, they were able to narrow themselves from, I think it was 500 material that they could use for a more efficient car batteries, and they narrowed down to about 10 best performing material, and they have to take that to the lab and actually now design the material. AI is finding a good place in the area of research, and especially in chemical engineering and material discovery. And I think this review compiled by Bayou is quite limited in essence, because I think it's probably just about 10 or 20 publications that he was able to pull, but I know there's quite a lot out more than that. Did I transition to the next screen?
Well, I think it's in the on the old screen.
All right. Next time on my FI.
Yeah. No, new screen.
It's the new screen.
Yeah.
Okay, awesome. Yeah, I think Google Meet is quite slow. Well, how do you go about solving a machine learning problem? If you are about what machine learning is, come on, we want to just talk about how do we go about handling a problem using machine learning. Well, the key thing to solving every problem is figuring out what exactly the problem is that you want to solve. So you start off with what we like to call a business understanding, right? What is the business I want to solve? Who am I solving that business problem for? For instance, are they formulating the problem the right way, or do I have to reformulate that problem? And then once you have that, the next question you have to ask yourself is, what data do I have? Because the data is the blood of your machine learning model. So you need to make sure you have that. is the data accessible? What type of data it is? How big is the data set? Is it small, a small data set, or some huge data? For instance, if you have a data about 1 million rows of data, it will be hard to actually simulate that on a computer that has very small memory. It will take you weeks for your models to converge. So knowing that information helps you decide on infrastructure for training your machine learning model. Then the next thing you're going to have to do is, what do I need to do? I need to prepare the data. Is my data clean? Are they missing? Are they biased? Do I need to convert some text to some numericals? So if you are familiar with categorical variables in your analysis, it's the same way. You're going to have to convert certain to categorical variables and all that. You need to come up with a way of figuring out, what the outliers. So this is where things like your box plot analysis and stuff become useful to you to be able to figure out, what are the outliers in the data set. Then from there, you move on to what we call the feature engineering. Now, feature engineering is really more of, saying like, can I create new information based on the data I have? So for instance, if I'm dealing with a gas system and I'm trying to model that system, but then I realize that, if you remember a very simple gas equation, equal to nRT, right, seems to apply. That is some information that is useful to you if you're an engineer of that system. But then if you understand that the system isn't that ideal and it's a real system, then it's not necessarily a PV equal to nRT. It's probably some exponential factors that might come into play. So that alone is enough information to say, okay, you know what, I'm going to take these pressure values and I'm trying to some sort of exponential functions, right? And that becomes new information in your data set that your model can use to learn. Target variation. You sort of need to understand in the more regression analysis where you are trying to predict a target variable like a flow rate. You want to understand what is my flow rate linear or is it exponential? From whatever you have to an exponential function to be able to help your get more good at it. So using that domain knowledge is very key. And then your dimensionality reduction comes to that stage too, because if you have 5 parameters, then it doesn't really even matter. You can just use a simple feature selection. But if you have several parameters, then it becomes an issue. Then deciding on the model that you want to use, ask yourself, am I doing what we call classification? So classification just means that my target variable have different classes or different group. And so in that case, I'm not just predicting what flow rate is. Sometimes it might be a flow rate that I'm predicting. Sometimes it might be something totally different outside of flow rate. A more classical example would be, you're trying to build a model that can predict whether a certain patient has cancer or doesn't have cancer, right? So that's a simple classification, generally called binary classification problem that you want to solve. Or I might solve like a regression model, and that will also help you figure out which sort of models to use and how to structure your algorithm to be able to solve the problem. I'm not doing clustering. Then you move on to the feature selection. The feature selection becomes, you cannot just handpick and say that, okay, well, because I'm trying to figure out what flow rate is, I just need pressure, and then maybe pump speed or something like that. You cannot just handpick that. That would be introducing some level of bias into your model. But what you want to do is you want the data to, the model to inform you that, hey, these are the useful information you actually need outside of all the information you have. And there are different strategies to do that. He has sort of just mentioned these a few ones which is commonly used in the industry, the Baruta and the Baruta-Sharpe algorithms. We have what we call stepwise selections methods that we commonly use out there in the industry. Then once you do that, another thing in machine learning is that you don't want to sort of say, hey, I just want to go and build a neural network. Because sometimes the problem you are trying to solve might not be best modeled by a neural network. It actually might be best modeled by some tree-based learning, like extra gradient boosting or a random forest model. So in that case, what you do is you create an ensemble of models, which just means that you put a lot of different models together, a basket of models, and you ask, you program your algorithm, tell it, hey, go train all these models, tell me which one is good. There are also auto ML packages out there, mostly in the Python libraries that you could go and choose whichever you want to use. And once you have your model selected, which you can do that in a very crude way, is that you don't optimize any of those models, and you just tell them which one is best based on in their unoptimized state. And then you go and optimize the best model. And that's if you are limited by computational resources. But if you have a lot of computational resources, ideally what you want to do is you want those basket of models and you want to optimize as the best performance. The best performance here might be assessed in different ways, and I think we'll talk about that in the next box. But optimization here is talking about parameter tuning. So when we are dealing with a neural network, which most of us be with, do I just need a network, perceptron, which is just one neuron, or do I a two-layer neuron? Maybe each layer have.
On the you are still on
page 7. Page 7.
All right, thank you.
Yeah. And basically then you tune it for things like what is the learning rate, how fast I call it the model to learn, and those you might come up with something that you are thinking you need like a very heavy model, or you might end up with a very simple model to solve your problem for you. So optimization is very important. Yes. Then when you come to performance criteria use in what the model to optimize for. So for regression analysis, you might be optimizing for things like accuracy, or you might be optimizing for error or the root mean square error. So for instance, if you're trying to predict your flow rate, you might want to get as accurate as possible measure. So you want to minimize the error measuring that. If you are dealing with more classification cases, like what I said about predicting, a patient has cancer or no cancer, you might want to optimize around what we call a precision or what we call a recall. Precision basically in machine learning just means that if your model says that the person has cancer, you want to make the person actually have cancer. So you want to show you are very accurate in saying that this person has cancer. A recall, in other words, is more like, I don't want to miss out if a person has cancer, right? So I might try to say that I want to be exact that this person has cancer. And by trying to narrow myself down, I think next time we should use Zoom or what do you call it, Teams, because I think Google Meet is slow. Is it there?
Not yet. Okay.
Okay, finally. Okay. And please don't hesitate to interrupt with questions if you do have some, so that we don't wait till the end. Okay, so this is an aspect of areas where like ML is actually used in process engineering. And if you are more interested in reading a lot, I think these guys wrote quite a very nice paper about these applications in process engineering. Tonetel, Artificial Intelligence in Process Engineering. I think I have the 4 references at the end of this presentation. I encourage that if you're a chemical engineer, you kind of read some of those things and figure out how you can start applying this even whilst you are in school. So most areas that they have identified is extracting meaningful features from raw data. So like basically like noise removal, signal filtering, and stuff like that. You can use AI to do that. Some people use it to augment control measurements. So as more like a filter on top of a control measurement. You could also use machine learning to do that. You can use it to predict like your process measurement outcome, like we talked about in the case of what do you call it, our flow rate. And you can also use this in what you call fault detections. So let's say you have a pump that is operating, and let me give a practical case where we did this back in my days in aviation. Was more like we were interested in understanding if we can alert an airline that, hey, a particular engine on your aircraft is about to fail. So take active maintenance. Because I don't think any of us want to see an engine shut down when we are in a plane in the middle of the air. And this was one of the things that we faced as a company at the time, was that failure. And this was kind of at a critical aspect of the power plant, right behind after the combustor. So in front of the combustor, we had a high turbine. So right behind that turbine, there was a seal, because part of the air that comes out of the combustor is extracted to inside the cabin for heating and cooling. And that seal was sort of leaking. Now, one, we had not understood it from engineering standpoint, what was causing this seal to leak. And 2, the FAA, which is the Federal Aviation of the US, is going to be on your neck that you cannot let an engine like that get in the air. So then it becomes a problem of how can I quickly solve this? So as a team of data scientists, we develop an in-house algorithms to go figure out if we can solve this problem using some sort of evolution optimization strategies. And I think in this case, we use particle swarm optimization to solve that problem. So machine learning can, and that was where I actually realized the true power of machine learning. Because what happened was, there wasn't an area that I have expertise in. And so what we did was, we trained a machine learning model to go and tell us which of the features were important. So if you remember the feature selection we talked about, then when we selected those features, we convened a meeting with the chief engineers who were expert in that component to review the results with them. And it was there that they realized what the root cause of the issue might be. In other words, you can use machine learning to actually teach you physics, because all the information is inside the data. And sometimes we are limited on how much we understand the data. And that machine learning can actually help you derive what the real information is that is contained in that data. And that became a very useful and successful use case for that company. You could also use it in other areas like process control, like I talked about, like signal filtering. You can use them in like things like in edge computing, which just means that you onboard a machine learning at exactly where your process is going on, so that your machine learning is not just, on some cloud waiting for some data, but it's just right, incorporated into the system itself. So it's able to take real-time actions, provide a feedback to your control to correct itself based on the information that is receiving. Another paper that I found useful that you guys might be interested in is this paper by is it Zingiang? Not sure what the exact name is. Is they also examine how they could use machine learning in the production of terephthalic acid in controlling flow rates and correcting for flow rate for that case. So with that, I'm leaving us about 40 minutes so we can ask questions and interact.
No, thank you, Marcus, for such a nice presentation. So maybe the first question that I will ask is, what do you recommend should be the best platform to be used, let's say for a learner who wants to venture into machine learning? Where do you think it would be the best place to start from? If it's going to be self-learning and you don't, are not going to go through a tutored program?
Okay, yeah, that's a good question. So AI is becoming highly democratized, and the good thing is also about that is that it makes information readily available. So there are many platforms that you could learn from. One that I highly recommend to people is Udemy. It's a low cost platform. It's not entirely free because people spend some time to prepare the lecture notes and upload it there. The good thing about Udemy that I recommend to people, I think a class in Udemy is about $10 or $9. You can get an entire class. So for instance, if you are interested in learning classification machine learning, you can learn the entire thing for just $10. It's more like, not necessarily just independent learning, because a full lecture that a person is taking you through, and you have access to ask the questions to with the person. So you can simply email the person. Normally they'll provide an email or some ways to contact them. So if you have questions, you email them, they are quick to respond to you. That is one platform I would say. Another platform that I recommend, which is probably the most published platform in the space of machine learning, is Medium. So if you go to medium.com, Medium though takes a $5 fee a month. So if you are interested in learning, you could just go and pay that $5 fee, and you have access to a lot of articles published about machine learning. So back to how to do principal component analysis, how to do feature selection. So you have access to all the information that at your disposal that you can learn. The only thing about that platform is there's no one person that you can say, hey, this person is going to answer questions to me. But if you post a question there, people are going to respond to you and they will answer for you. Another platform
Chrysler, Steve. Maybe Mark, go first, and after Steve can ask his question.
Okay, thank you very much, Doc. And thank you, Engineer, for the wonderful presentation. I really learned a lot. And please, about the feature extraction, do you mostly, how do we do it? Do you mostly, let's say, pick just one? Let's say I have, about 12 inputs and then one output. So will I pick just one input, then I'll be checking at each of them with the output, or maybe I'll be doing combinations of the inputs and I'll be doing with the output to see which features are very important. And also about the principal component analysis, my research, I did some modeling for my MPhil work, and then I saw that when I use principal component analysis, I saw that the error, the root mean squared error, I was using MATLAB, the regression learner app in MATLAB, and I saw that the root mean squared error was going up if I use principal component analysis. But without the principal component analysis feature, I saw that my error was better compared to when using it. So does it mean that over here, all my input variables are very important in terms of training the model?
Okay, no, that's definitely a great question. In terms of feature selection, you are right. Generally, that's how you do it. Well, you don't have to do that yourself because there are a lot of Python libraries that do them for you. But behind the scene, that's what they do. So if you remember in the presentation, I talked about stepwise selection. That is exactly what stepwise selection does. What it does is basically you build a regression model in a regression process. So for instance, I take one parameter, I build a model, which is basically y equal to mx plus c model, right? Then I add a new parameter to that, right? I figure out what is my error for prediction, right? Then I add a new parameter to that. Now my model is equal to y is equal to, mx1 plus nx2 plus c. Then I build that new model, and then I figure out what is my prediction error again. So in each stage, you are doing training and prediction. You train and you predict. Now, when I add a new parameter, I'm interested in figuring out, has that changed the error for my first parameter after I build a model with the first parameter? So called a simple model 1. Now I have another model 2, which is a little complex. Has that changed the error? If it hasn't changed it enough, then it means that a second parameter is not that useful, right, in predicting what y is, right? So I don't need that. But you have to also define a threshold for what is change, right? Because in computation, 0.001 is a change. That might not honestly be meaningful, right? So you sort of figure a threshold to say that, okay, if the error changed by this threshold, then yes, I need to keep that second parameter. Then you keep doing that. So what you end up is, if you have 10 parameters, then you have, y is equal to x1 up to x10. At some stage, you realize that when you add new parameters, it might not be changing the error in measuring your y. So in that case, those parameters are not important anymore. Now, if we go out of that space, which is stepwise selection processes, and we look into the Baruta-Sharpe and the Baruta algorithms, the Baruta algorithms are quite different, right? The Baruta algorithm is basically, in itself, what they are trying to figure out is, are the parameters you have better than a random guess, right? So random guess is, any probability that's 50, or below, it's like a random guess. If you flip a coin, your probability of getting a head is 50 or a tail is 50. It's a random guess. Now, Baruta-Sharpe is saying that, okay, if a particular parameter or input has an effect that is better than a random guess, then it's probably good for the model. So what they do, how do you measure that? What they do is you take a parameter, you keep a copy of that original parameter, you create a pseudo version of that parameter, right? And you shuffle it. So just create a copy of that parameter, you shuffle it. When you shuffle, what you do is you disconnect the relationship between that shuffled parameter and your input, and your predictor, which is your y, right? Because you didn't shuffle the y, so your y information is kind of constant, but you shuffle a copy of your x. Now you figure out if the x performs better than its copy, so the copy becomes a random guess, then x is useful to the model. If it doesn't perform better than its copy, which is a random guess, then x is not useful to the model. So that's like behind the scene, that's what Baruta-Sharpe does. The good thing is you don't have to go in and program this yourself. Then when we come to your PCA question, so when I was talking, I talked about PCA doesn't retain 100% of your original information. So when you do a principal component analysis, let's say you have 10 inputs in your data set, and you do a principal component analysis, you have to ask yourself, how many components do I need to retain a certain percentage of information in the original data sets? So principal component is more like a translation. You're basically translating from 10 dimensions to a certain X dimension. The question you ask yourself is, what are X dimensions? Is it just 2 dimensions? Is it 3 dimensions? Is it 4 dimensions? Is it 5 dimensions? So that's the question you have to ask yourself. How do you figure out what is that new dimensions? That is where you figure out the percentage of information retained based on number of components. So if you didn't code this by yourself and use like some of the Python packages, you should be able to retrieve something called contribution. I think it's called contribution or something like percentage contribution or something like that. Then that would tell you that, okay, if I translate my information from 10 dimensions to 2 dimensions, the 2 dimensions will only contain about 60% of the 10 dimensions. So what is going to happen is, if I now use those 2 dimensions to build a model, it's not going to do as well as the 10 dimension because it's only giving me 60% of the information, the data. If I take it to 5 dimensions, then I'll start increasing more information. So it's also more of an optimization in itself. I wonder if you did anything like that. Did you translate this to 2 dimensions, 3 dimensions? Like, what was your principal, the number of principal components that you ended up with in building your model?
Okay, and I realized that when I used about 98% of the variance of the model for the PCLs, they selected about 5 out of the, let's say, 12 input variables. And then they gave their percentages in terms of how important each of them are. Okay.
Yep. And how did that perform relative to using all the 12 variables?
Yeah, I think the difference was very small, but in all cases, in changing the percentage, I realized that using 100%, meaning that not using any PCA, was giving me the best mean squared error and R squared compared to using the PCA. So I decided not to use the PCA.
And okay, so was that based on your test data or your training data? When you say the best root mean square, is that based on your test data or your training data?
Okay, it was based mostly on the training data before the test data came in.
Okay, so one thing to take note is, when you are training a machine learning model, you never want to make the assessment based on the training data.
Okay.
Yeah, because the reason being that is the model tend to memorize the training data. And so it's able to recall that information quickly. I remember when I talked about memorization and overtraining. So when you do that, you are getting an artificial sort of performance assessment. It's not a true performance assessment. And that's why we generally do the traditional train test split in your data set. So you split the data into 2, say 80% I'm going to use to train the model, and I'm going to keep 20% to test when after I train the model. The training performance might be good. The training performance is just good for deciding convergence of your model. But assessing the true performance of model is not going to be based on your test performance. So I don't know, if you have some chance, you can test that out and see how your PCA-based model does on the test data, and then the non-PCA does on the test data. It's likely that the results are going to be very close.
Okay. And please, what about cross-validation? Can cross-validation reduce the overfitting issue? Because I was using about a maximum cross-validation based on the number of data points I was using.
Yes, cross-validation can what do you call it, can reduce overfitting. The trick about cross-validation is that if your data size is very small, and then you are not doing a repeated sampling, then it's likely that on each training set, you are having less data to train a model. And the less data you have, the difficult it is for the model to learn. Think about it like a function and the domain of a function, right? If you sample from the domain of the function to define the function, it's going to be different from if you use the entire domain of that function to define it, right? So when you are doing cross-validation and you're sampling and training and testing, sampling and training and testing, you are basically sampling from the different domains. And if you don't have a lot of data, hello, can you hear me?
Yeah, yes, I can hear you now.
Oh, okay. So if you don't have enough data within all aspects of the domain to train and test, then there's going to be one aspect you do well, and then a lot of aspects probably your model doesn't do well, and it doesn't also help. But if you have a lot of data set, then cross-validation helps you in reducing overfitting.
No, thank you. I think another hand is raising. The name of the person starts with Y. Please, you can ask your question. Whoever you are.
I actually think it's the same person.
No. I think your boy is the one who just asked.
Okay, then Kwame. I see some Kwame hands raising. Hello, Kwame, unmute and ask your question. Okay, it looks like Kwame cannot hear us. Guys, any other question? Hello, it's Richard here. Jero.
Yes, Doc, I am here.
Please, no, take over your role as our MC.
Sure, thank you for stepping in.
I have a question.
Okay, yeah, well, go ahead.
Yeah, I wanted to know if the type of, in terms you have, let's say, categorical variables, if you are using different forms to, let's say, change it to numerical variable. Let's say I'm using label encoding.
Yeah.
And then let's say maybe custom encoding. Is it possible that I'll have different results if I use different form of encoding to change the categorical variables to numerical variables?
Yes, it would. Because what happens is if you just use label encoding and what do you call it? You translate, let's say your categories are more than 2, right? If they are just 2, then it becomes easier. You can transform that to a Boolean. So just 0 and 1s, right? But now 0, 1, 2. In modeling, the model is going to think that 2 is more meaningful than 1, right? And 0. So it will affect how the model understands that particular parameter. So in that case, what you probably want to do is you can sort of translate those categories into new columns. So you have what do you call it? Column that is called category 1, category 2, category 3, and then those you just set them to 0, where in the rows of your data where that category is not present, you set it to 0, where it's present, set it to 1. So it's kind of create Boolean. If the categories are too many, sometimes you could have up to, I remember I worked on a problem for optimizing ship construction for one of the US Navy shipyards. And we're trying to optimize decision-making in the construction process. And they had a lot of categorical variables, and one of the categories had almost, I think, about 200 categories. So it becomes very hard to use, simple encodings. What became useful was, I don't know if you heard about CatBoost encoding, but
no, please.
Yeah, so CADBoost encoding is probably one of the most efficient encoding algorithm that I have used before. Because it doesn't just translate them to, let's say, category 1, I'll call it 0, category 2 is 1, category all the way to like 200. It doesn't do that. It basically uses sort of frequency of occurrence of a category, right, relative to your target variable, and then it does some calculation. So you end up with some numerical numbers that relates with your target variable. In that case. So yeah, depending on which encoding method you use, you have totally different results.
And please, what's the name of the encoding you just talk about? I want to search for it.
CADBoost, like a cat, C-A-T, and then B-O-O-S-T, CADBoost encoding.
Okay, thank you very much.
Yep, you're welcome. Any other questions?
Yeah. Are there any other questions? Caleb?
I think Caleb raised his hand.
Yeah, Caleb, please go ahead.
Good evening, everyone. Okay, Engineer Marcus, I want to ask a question about the training for machine learning and artificial intelligence. For how long or how consistent should you be to, or which stage should you reach before you say, okay, now I want to give myself a little break or work on these models so that you don't lose your skills? Or should you just do it till you become a master? Or I don't know if you get the question clearly.
Yes. So you are talking about the learning pipeline.
Yes.
Yeah. You know, I think that they're saying that training makes a man perfect. You know, it's true, and I think it's always going to be true. So the more problems you solve, the more you're going to learn. So I would say that get the basics and start from there. So I think almost every science student in Ghana, I would say, probably has done machine learning before. Just that in those days, we didn't call it machine learning, we call it regression, right? Because if you remember, we started building y is equal to mx plus c models back at JSS. So we already have that basics, right? And we know how to calculate root mean square and all that, right? So we already have all that. So just start figuring out, okay, how do I incorporate the computer aspect of it to actually now implement those solutions and whatever problems you have. And there's a lot of data set. I think a popular data set called like University of California machine learning data set. I'll get the exact URL to that data repository to reach it so he can share with you guys. But that is a good place to sort of to get a lot of data set that you can learn along. Any algorithm you learn, you can go in and figure out which data set fit into that algorithm, and you try to actually train practically with it.
Thank you very much. Thank you very much.
Yep, you're welcome. And I think Yabua has his hand up.
Yeah, I was checking something. My research area is in convergence of biotechnology and machine learning. So for my effort research, I use custom encoding for the microorganisms. But I wanted to see, is it possible to use the CADBoost for, in terms of, I have 3 microorganisms in the bioreactor. Can I use the CADBoost to help encode it better in order to give better understanding to the model for good predictions?
So are you talking about encoding the 3 organisms in this case? Organism 1, organism 2, organism 3. I think in this case, I probably wouldn't use CADBoost because that is a very small set of categories. So I think I'll probably just convert them to Booleans. And the way you do that is you just create new columns in your data, train new columns, and then wherever your organism 1 is, or let's say column 1 is organism 1, column 2 is organism 2, column 3 is organism 3. So in column 1, whichever row organism 1 is, you just put 1 there. Whichever row there's no organism 1, you put that 0. And then you do the same, column 2, whichever organism. So when you do that, what do you call it? You are basically telling the model that, okay, in row 1, I'm dealing with data for organism 1, so it's 1. So organism 2, organism 3 columns are set to 0, 0, right? And you do that for all the columns because you have just few categories and it doesn't change the dimensions of your data that much.
Okay,
but normally when you have more, then you get more.
My microorganisms were having 18 different microorganisms. I have 18 different microorganisms in the data set. So, but there are, let's say, 2 or more microorganisms in one data point. So there are some data points that have 2 microorganisms, some have 3 microorganisms. So in situations like that, if I'm to use all the 18 and say that, okay, for this one, there's only 2, then it will make my data set very large. Or
yes, yeah. In that case, yes, that's you'll be increasing your dimensions too high. So I don't think that's probably the right place. In that case, you could use the CatBoost encoder.
Okay. And the CatBoost, is there any maybe app or something that can help me do it easily if I put in, let's say, the microorganisms and they will generate for me?
Yes. So, you said you did your work on which platform? MATLAB.
Yes, please.
Yeah. So I would suggest you look up how to use CatBoost encoder in MATLAB. There probably has been some use cases out there. If it was in Python, you probably don't need to do any of that. I would say, and I think I could actually share some code with you in Python on how to use CatBoost encoding. But I haven't done machine learning in MATLAB. I only use MATLAB in my optimization class. That was it. So I can't tell much about MATLAB. But yeah, when it comes to Python, there are a lot of information that you don't need to do much work. You just import a library and put in the data and tell it to use CatBoost for this particular column, and that's all you need to do.
Okay, thank you very much.
Yep, you're welcome.
Okay, so I think is this Simon A?
Simon.
Yes, Simon, go ahead.
Yes. It's good evening. I would love to know your opinion on this. Would you rather a master of one skill or a jack of all trades, and why do you say so?
A master of one skill and a jack of all trades. That's a nice question. Why do I say it's a nice question? If you notice my background, I'm a chemical engineer by heart, right? And I did my master's in chemical, but my first job was in aviation. And I remember when I was interviewing, the person interviewing me was the director for propulsion analysis, Dr. Brogan. And at the end of the interview, I asked Dr. Brogan, why do you want to hire me? And that is, he told me that was very rare because a candidate never asks the employer, why do you want to hire me? And I said, well, because I'm a chemical engineer, I don't see, how valuable I'll be in aviation. And then he told me, well, simple and short, I think you have very strong thermodynamics background, and that's what we need for jet engines, right? And when I got there, I realized that not only was it just thermodynamics that was useful, but my fluid mechanics was useful. My reaction engineering was useful because there's the combustion aspect of the jet engines, right? And then I realized I didn't know anything about modeling, in terms of coding. So I started learning about coding. And when I learned about coding, I realized how efficient I became in my job because it's just a tool. Programming is just a tool. It's nothing beyond that. Right? How you use that tool is probably what sets you apart, right? And I got excited about that. And that's how I pivoted into data science. And then I added machine learning. And then I added pharmaceuticals. And I went to, production automations. So all that to say that knowledge in itself is additive. So it doesn't really matter, but make sure that at each stage of your life, not your life necessarily, but in your learning process, you have an area where you want to be known for. So having that level of specialty is good, but just constraining yourself narrowly to that can be bad at sometimes, because then it means that you are only useful in that area, and when that area is not there, then you become less useful. So you want to learn and broaden your mind as much as possible, but have an area that you can say that, okay, this is an area people will say, oh, this guy is good at this. So there's no clear-cut yes or no to that question.
Okay, so I think there's a few hands. So yeah, the next person could ask the question. What's the name? Sana.
Yes,
Sana, please go
Shaibu.
ahead.
Or Alexander, whoever is already, Ando.
Yeah, I also wanted to ask, have you ever encountered a scenario where a model you've trained to do a specific task has failed?
Yes.
And when it happens, what are some of the measures you take to tackle the situation?
Yes. Right. What sort of information have I measured? So you might have a lot of data, but the data might not necessarily be good for answering a particular problem. In which case you can't do much about it, because it's like trying to get somebody to walk without providing them air, and so they cannot breathe, so they are basically lying down, choked. So yeah, there are instances like that. In that case, you don't beat up yourself. You just try to understand why this problem cannot be modeled by machine learning models. Does that help?
Please, thanks.
Yep, you're welcome.
Please, any more questions? So, Mactus, I have one question here.
Yes.
Hello, Mactus.
Yes, Jude.
Like, usually we think of machine learning as an opaque or a black box kind of modeling, right? So my question is, like, what role does theory, let's say theory of the field in which you are trying to model, or an understanding of the field, what role does that play in trying to develop good machine learning models?
Yes, I think it plays a huge role. I think if you remember from the slides I was showing, I talked about domain knowledge. Because and how domain knowledge can help you make better feature engineering, right? So part of the process is not just feature selection, there's also the feature engineering aspect. So I have these measure, can I create new measurement out of those measurements? And based on your expertise in that field, you can say that, well, like what I was saying, you can say that, well, I have a temperature, but for this particular system, the likely relationship between the measurement I'm trying to predict and temperature is actually some exponential function. So let's say t to the power. So based on that information, you can create a new feature, which is, the root square of your t, right? To add to your model. So that's where domain knowledge becomes super useful. And I think as a machine learning engineer, if you are solving problems in an area that you have limited domain knowledge, which most likely if you are feeling just AI, you're gonna have those issues. You have a responsibility to work closely with the domain experts. So if I'm solving a machine learning problem, I don't solve it in isolation, you know. And one thing I've noticed is we scientists and physicists, we love our physics models. We love our physics models, and you know, beginning we say machine learning models are garbage. So you work closely with them, try to understand exactly like the problem, you know, what is the expected relationship between this variable and, you know, like what we are trying to predict. You know, are there other things that is probably not in the data, right? So you ask yourself all those questions, and that you can derive new information. And sometimes you could even have to simulate, or if you have a model of that physical system, you can actually simulate those new features, right? And add them to your data set. But you can't do that if you don't have the domain understanding of the problem you're trying to solve. So it's very critical to have domain.
You know, in this field that he spoke to us about, please, we'll come knocking again. I like the way you were saying that next time we should use, you yourself, you were thinking next time, no.
No.
That's the good feature. No, that is a good feature that, no. So you are giving us a green light that, no, we are allowed to come next time, and we will definitely use that door. So please, we'll be looking forward to all the other files that you say you share with Richard, and we're very thankful. Please, anytime you are in Ghana, I say this because it's mostly based in the US. We might also, I don't know, like an in-person lecture, if that is possible. So no, we want to thank you for this beautiful lecture. No, I've learned so much from it, and I know how to navigate my machine learning journey, which is not as extensive and as deep as yours. No, thank you. Thanks a lot.
No, thank you so much. I'm always happy to connect and share. For me, it's a learning process for all of us. And you know, when we learn together, we grow together, and we sort of build each other up. So thanks for putting this together, and I'm quite excited that, you know, Aaron is taking the initiative to incorporate this field into the knowledge base, because it's really what is going to make you marketable outside there. I think we have all seen things like ChatGPT come up. If you in the US, in the industries, it's probably the biggest thing going on now, where we actually use it. For context, I built an entire AI technology just from ChatGPT, right? I had zero knowledge in NLPs, and I built an entire NLP technology world with it, just using ChatGPT. What that is saying is that the field of engineering is actually what do you call it, transforming so fast, even though we are not seeing it. And at some point, the most brilliant engineer is not going to be the person who knows most of the equations. It's probably going to be the person who knows how to use AI the most.
No, definitely.
Yeah.
Definitely. No. Thanks a lot. Please, is NLP a nonlinear programming, the NLP you built? Or is something else? You said you built an NLP.
No, not nonlinear. That's natural language processing. Sorry.
Yes.
Nice. Yeah, natural language processing, not nonlinear programming.
Oh, no.
Yeah, but you could actually incorporate nonlinear programming into machine learning. So we have what we call physics-based machine learning, right? Which is sort of a new field, which is probably the most I think that's probably going to be the most practical way to apply AI in the field of engineering, is that you sort of try to incorporate the physics. For instance, if I'm dealing with a fluid system and I realize that, okay, I can use the Navier-Stokes equation to solve that fluid system, I can actually use the machine learning to optimize the Navier-Stokes equation. You see, so it's sort of and if you can write out your NLP, your linear programming stuff into sort of equation, you want to optimize that, you can actually use the machine learning to help you optimize the solution for that your linear program. So yeah, I haven't done that, but I know somebody who has done that before, Yash, a consultant who I've worked with some time ago.
Oh, thanks a lot once again. We will definitely fall back on your expertise. Yeah. So you see, everything you are saying, we agree that the ground beneath our feet is shifting so fast. You have to find ways of catching up. But when we have a bureaucratic system, it makes it not easy. So platforms like this become some of the ways in which we do catch up. So no, please, thanks for availing yourself. We'll come knocking on your door once again.
Definitely. Yeah. Thank you too. And I wish you all the best. And don't hesitate to reach out through LinkedIn if you have any questions.
Thank you. We will reach out.
All right. Bye-bye. And thanks you all for your attention.
No, thanks. Yeah.
Bye.
Thank you very much.
Richard.
Thank you
Yep.
for organizing it.
You too. Bye.
Oh, no, thanks, Ernest, yeah, thanks for holding us down, yeah. People like you showing up also gives it more credence and everything, no. Thanks, I know we hope to do more of this. So guys, we will let you know what our plans are going forward. Oh, thanks everyone.
Sure. Thank you.
Yep. All right. Bye.
Can David, are you sharing something?